Now we will see some questions on organic nitrogen compounds. First one is as starting from the isomeric numbers. First question reads in this fashion: the number of structural isomers possible for the molecular formula C3H9N is, they have given 4 choices, 5, 2, 3, 4. Now C3H9N means it contains carbon, hydrogen and nitrogen. So organic nitrogen compounds containing only carbon, nitrogen and hydrogen may be amines. So amines formula RNH2. So here it contains 3 carbon system. So amines with 3 carbons, CH3, CH2, CH2, NH2. This is called propylamine. So in this propylamine there are 3 isomers possible: N-propyl, isopropyl and NN-dimethylamine. How the methyl groups are attached? So this is called N-propyl. So let us first check the molecular formula whether it is correct or not. C1, 2, 3, C3, H3, 5, 7, 9, H9, N, only 1 nitrogen. So molecular formula is correct, our assumption is correct partly. So amines, there are 3 types of amines we know: primary amine, secondary amine and tertiary amine, and also how it is substituted. So this is called N-propanamine or merely propanamine. Now it can be written as this 2 isopropylamine, CH3, CH, NH2. Here also 1, 2, 3, C3, 3, 6, 7, 9, H9, N. This is also isopropylamine. It is there are 2 primary amines are possible for this system. Generally for any amine, primary amine, secondary amine and tertiary amine will be possible. Here even for the simplest one, primary amine itself, N-propylamine, isopropylamine. Isopropylamine, if you see the structure, 2 aminopropane. It is called 2 aminopropane. First one can be written as 1 aminopropane. 1, 2, 3. 1 aminopropane, 2 aminopropane. 2 aminopropane is also primary amine because it contains the structure NH2, NH2. So there are 2 primary amines possible. 2 numbers of primary amines possible. Then secondary amine. In these cases, amino group is attached to carbon. Next, what happens to the methyl group? So there is one another compound called N-methyl ethanamine. N-methyl ethanamine. Ethanamine means CH3, CH2, NH2. There are 2 eth means 2 carbon, 1, 2 amine. Here nitrogen, in nitrogen 1 methyl group is there, that is meant by N-methyl methanamine. Let us check this formula also. 1, 2, 3, C3, 3, 5, 6, 9. C3H9 N is possible. Last isomer is that both the methyl groups are present on this one, that is CH3 N, CH3, CH3. So this is CH3NH2 is methanamine. This methanamine, 1 nitrogen itself, 2 methyl groups are there. This is called NN-dimethyl methanamine. NN-dimethyl methanamine. Just for understanding and revising, we have given totally primary amine 2 numbers are possible. Secondary amine 1 number is possible. Tertiary amine 1 number is possible. 1, 2, 3, 4. 4 types of amines are possible. So for the current question, correct answer is 4. Once again, to repeat the current question along with the answer, the number of structure, all these are, they differ in the structure. Amino group is attached to carbon group. Alkyl group is attached to nitrogen group. One alkyl group is attached to nitrogen group. Two alkyl groups are attached to nitrogen group. That is to be noted. So here primary amine, secondary amine, tertiary amine all are possible, but secondary and tertiary only one type. Primary amine there are two types of primary amine. So totally 4 amines are possible. So the number, to repeat this question along with the answer, correct answer, the number of structural isomers possible with the molecular formula C3H9N is 4. This finishes the current question and its answer. Now we will see the next question, second question. So second question is based on the reactivity, preparation of amines. So here this question reads in this fashion: the method by which C6H5NH2, that is aminobenzene or phenylamine, C6H5NH2 or amino cannot be prepared. So the method by which, even though we suggest many general methods for preparation of amines, some methods are not cannot be applied for some amines. That is the limitation that they are asking. Method by which phenylamine or benzamine or aminobenzene cannot be prepared is, they have given 4 types of reaction, 2 mentioned as named reaction, 2 mentioned as equation. So first one, Hoffman's degradation. Hoffman's degradation. Hoffman's degradation is that bromine KOH from amide we can prepare amine. So amine with less number of carbon atom can be prepared. We have seen the equation. Acetamide on reaction with bromine KOH forms methylamine. So this is possible. Second method, by the reduction of nitrobenzene. Reduction. So it is also possible. Nitrobenzene or phenyl nitrate, when it is reduced with tin HCl, it forms aminobenzene, C6H5NH2. So nitrobenzene can be reduced to aminobenzene. Second method is also possible. Third one, Gabriel synthesis. So Gabriel synthesis involves this one, that is phthalic anhydride reacting with KOH. This is called phthalimide, phthalic anhydride. The oxygen group of phthalic anhydride is replaced by NH. This reaction we have seen. This phthalimide reacts with KOH. KOH replaces, it forms potassium phthalimide. This potassium phthalimide is reacted with alkyl halide, etc. So here alkyl halide. But this reaction cannot be used for here because starting material, which material we want? Phenylamine. Up to this we can proceed, but phenyl bromide cannot react here. Aromatic compounds, so you cannot eliminate KBr and form this type of substituted derivative NC6H5. So this compound cannot be obtained. Potassium, up to potassium phthalimide we can get. Then afterwards, from this it is not possible to get the phenyl derivative. Only if we get phenyl derivative, that can be further hydrolyzed to form phenylamine. If it is hydrolyzed, you can get phenylamine, that is C6H5NH2. C6H5NH2. But here limitation arises, phenyl derivative is not possible. So Gabriel synthesis cannot be applied to aromatic systems with nucleophilic. Here the nucleophilic substitution cannot take place easily with aromatic systems. So this is the limitation. So Gabriel synthesis cannot be applied to the preparation of phenylamine or aminobenzene. Last one, of course, that we have studied, that is C6H5NC. that is phenyl isocyanide, that can be hydrolyzed to form phenylamine in the presence of acid. That is, this is a general method. You can get C6H5NH2. It is possible with the, of course, here there is a loss of hydrogen, loss of carbon atom, number of carbon atom is reduced. That it is possible. You can get amines with less number of carbon atom from the starting material. So comparing these methods, Gabriel synthesis is not applicable because of the limitation of the nucleophilic substitution with the aromatic ring. So once again, to repeat the current question along with the answer is that the method by which aminobenzene or aniline cannot be prepared is Gabriel synthesis. All other methods can be prepared for the preparation of aminobenzene. This finishes the current question and its answer. Now the third question, it is based on the reaction. The components are mentioned in a figurative form like this. Here it is mentioned that the reaction C6H5NH2. So the reaction C6H5NH2 is aminobenzene. C6H5NH2 with this combo, that is ClCO C6H5. Actually it is mentioned in this fashion. Cl, a line, double bond O, which means that this compound is Cl, C, double bond C6H5. This is nothing but benzoyl chloride. Benzoyl chloride. So the reaction of aniline, aminobenzene or aniline, the reaction of aniline with benzoyl chloride in the presence of NaOH dispersed in water, aqueous solution of NaOH, is a derivative, that is C6H5NHCO C6H5. NHCO C6H5. This compound is called dash reaction. The question, to repeat once again, the reaction aniline plus benzoyl chloride in the presence of aqueous NaOH giving the compound C6H5 NHCO C6H5. Actually what is the name of the product is that C6H5NH2 is phenylamine. N-phenoxyphenylamine. So it is a complex compound. It is a direct. This reaction is given. What is the type of reaction? Choices are given. It is Perkins reaction. It is acylation reaction. It is Friedel-Crafts reaction. It is Scott-Baumann reaction. They have given. Which is the correct choice? It may appear everything to be correct, but Perkins reaction is associated with aromatic systems only for aldehydes. So Perkins reaction is not there. Acylation is the phenomenon of incorporation of this acyl group. Acyl group only to hydrocarbons it is possible. Acylation, not amino compounds. It is, of course, phenomenon is incorporation of this group is called acyl. RCO grouping is called acyl group. Incorporation not to hydrocarbon, it is for amines. So it is not also correct. Next one, Friedel-Crafts. Friedel-Crafts incorporates only alkyl groups, not acyl groups. This incorporates acyl groups but only to hydrocarbons. This incorporates alkyl groups and acyl groups once again to hydrocarbons. So it is not also correct. Scott-Baumann reaction is the correct choice because Scott-Baumann reaction, there is a compound, this amino compound, amino hydrogen is said to be active hydrogen. So a compound contains active hydrogen. What is meant by active hydrogen? Hydrogen attached to oxygen or hydrogen attached to nitrogen. These are called active. Whenever you write the reaction, first we eliminate only ROH plus Na giving. We write RONA plus H2. We do not disturb the hydrogen in the alkyl group. Here also NH2 reacts means hydrogen of amino group is first replaced. So they are more active than the alkyl group hydrogen. So this hydrogen atom attached to nitrogen or oxygen, they are said to be active hydrogen. Systems with active hydrogen such as amine, can be acylated in the presence of Friedel-Crafts catalyst is different, AlCl3. So here the catalyst is also different, NaOH. This is the Scott-Bauman reaction. So Scott-Bauman reaction uses aqueous NaOH to incorporate acyl group to compounds containing active hydrogen. Hydrocarbon does not contain active hydrogen. We cannot tell aromatic hydrocarbons will not contain active hydrogen, because aromatic hydrocarbon, there is a resonance phenomenon. They are somewhat tightly bound. They are not so easily active. So for the current question, correct choice is Scott-Bauman reaction. To repeat the question along with the correct choice, the reaction between aniline and benzoyl chloride in the presence of aqueous NaOH to get the N-acyl derivative. N-acyl derivative is Scott-Bauman reaction. This finishes the current question and its answer. Now, fourth question reads in this fashion. The electrolytic reduction of nitrobenzene in strongly acidic medium produces dash. They have given 4 choices. Some of them mentioned as figure structure, some of them in name. First choice is given as azoxybenzene. Azoxybenzene means C6H5. This 5 unit stands for C6H5. So C6H5N double bond N C6H5 coordinate linkage oxygen. Second compound is called azobenzene. That is C6H5N double bond N C6H5. Third compound is merely aniline or aminobenzene. That is C6H5NH2. Fourth compound is called para-aminophenol or 4-aminophenol. So phenol, if you number from phenol, 4-aminophenol or para-aminophenol. So here everything is based on the reduction concept. In the first one, C6H5NO2, from 2 molecules only one oxygen is or few oxygen is removed. So removal of oxygen is reduction. Second molecule, totally oxygen is removed, reduction. Third molecule, hydrogen is added. So removal of oxygen, addition of hydrogen. Third. Fourth one, removal of oxygen as well as addition of excess hydrogen. Addition of excess hydrogen. So it is a strongly acidic medium. Strongly acidic medium means first when nitrobenzene is reduced in strongly acidic medium, strong acid, in the presence of passage of electricity, electric current, electrolytic, initially it forms a compound called phenyl hydroxylamine. Already we have seen NH2OH is called hydroxylamine. This group is hydroxyl, this group is amine, so it is called hydroxylamine. This hydroxylamine, one hydrogen is replaced by phenyl group, so it is called phenyl hydroxylamine. This phenyl hydroxylamine undergoes rearrangement, so that it is the hydroxyl group goes to the benzene nucleus and the hydrogen comes here. So benzene hydrogen coming para position, benzene hydrogen from the para position coming to amino hydrogen, whereas hydroxyl group going to the para position, it forms para-aminophenol. So para-aminophenol is the correct choice for the current question. Once again, to repeat the question along with the correct answer, the electrolytic reduction of nitrobenzene in strongly acidic medium produces 4-aminophenol or para-aminophenol. This finishes the current question and its answer. Now, the fifth question reads in this fashion. Which of the following diazonium salts is the most stable? Which of the following diazonium salts is the most stable? Here, first one, methyl diazonium chloride. Second one, benzene diazonium chloride. Third one, ethyl diazonium chloride. Fourth one, it is called benzyl diazonium chloride. So this is all are diazonium. First one, methyl diazonium chloride. Second one, benzene diazonium chloride. Third one, ethyl diazonium chloride. Ethyl diazonium chloride. Fourth one, C6H5CH2 is called benzyl. So here already we have to remember the two important formula difference. C6H5CH2 is the benzyl group, BENZYL, whereas C6H5CO is benzoyl group. C6H5CO is called benzoyl group. Already we have worked some question on that. Now this is a different. Here, which of the following diazonium salt is the most stable? It is asked. We have also studied only for benzene diazonium chloride. So from this we see that benzene diazonium chloride is the most stable. Generally, aliphatic diazonium salts are not stable. Aliphatic diazonium compounds are highly reactive. So aromatic compounds are more stable than aliphatic compounds because benzene, the stabilized structure. So here this positive charge is moved to this, both are nitrogen only. Both are nitrogen. They are equally powerful. So the positive charge moves to here. If it moves to here, automatically this positive charge is stabilized in the benzene ring. So resonance structures are possible with the benzene ring. 6 carbon atoms are there. Here aliphatic carbon, aliphatic it cannot so easily move. If at all moves, it cannot get 6 resonating structure or 1 or 2. So here only 1 carbon atom. Ethyl contains 2 carbon atom. Next question, a question may arise. Fourth one is benzyl. It contains benzene unit, but it is not stick. It is a diazonium group is in the side chain. So here diazonium group in the benzene nucleus. So diazonium salt will be stable if it is attached to the most stable benzene ring, aromatic ring. Even it can be replaced by naphthalene. So other question may arise. So only benzene diazonium chloride is possible. Naphthalene diazonium chloride is also possible. Naphthalene, here it is revolved around 10 carbon atoms. So here the most stable system is aromatic. Aromatic systems, diazonium salts are stable. All other are aliphatic system. This is purely aliphatic. This is also ethyl diazonium chloride is also purely aliphatic. Aliphatic diazonium salts are highly reactive. The last choice is that it is not aromatic. It is aromatic substituted aliphatic diazonium. So here we have seen CH3. In this CH3, one hydrogen is replaced by phenyl group. That's all. So maybe it can be less reactive than methyl diazonium chloride, but it is more reactive than benzene diazonium chloride. So to repeat the current question and answer, the most stable diazonium salt among the given 4 choices is benzene diazonium chloride with the formula C6H5N2 plus Cl minus. This finishes the current question and its answer. Now next question. So next question is based on the coupling reaction. So benzene diazonium chloride. So we have seen that benzene diazonium chloride is highly useful in the manufacture of azo dyes. So they have given different azo dye intermediates or dye products, final dye stuffs, which is the correct one. So in the reaction, benzene diazonium chloride undergoing coupling with aniline in the presence of acid to give rise to a yellow colored dye of specified as A. If that is the case, the compound A is dash. They have given 4 choices. First one is called hydrazobenzene. N double bond N, C6H5 unit is called azobenzene. One hydrogen is there, so it is called hydrazobenzene. Hydrazobenzene. Second one, it is azobenzene, but 2-amino azobenzene. So see N5 is azobenzene, but there is aminobenzene, amino group in the ortho position, adjacent steric groups are there, it is less stable. It will not be so easily formed. First one, it is hydroxybenzene, it is less stable. You will see one by one, less stable. It is here the ortho group, steric effect is there. Third one is meta group. Once again, this is aminobenzene, but amino group is in the meta position. Amino group is in the meta position. Last one, aminobenzene, where the amino group is in the para position. Even if you write the reaction as such, C6H5N2Cl plus C6H5NH2, C6H5NH2. In this coupling reaction, only in coupling reaction, benzene hydrogen is undergoing removal, not the amino hydrogen. Benzene hydrogen is condensed as HCl. It forms this type of, if you remove HCl in this one, you will get N double bond N. There is a reactivity, it is shifting towards, so N double bond N, it forms para amino azobenzene, it is called. This unit is called azobenzene. In the para position, amino group, so it is called para amino azobenzene. So para amino azobenzene is the most stable product arising due to this reaction. So in the to repeat the current question and with the correct answer, this is the most stable form. So amino group, here this compound is not stable means this in this first compound nitrogen heavier. So here already nitrogen is in the double bond. Once again nitrogen is attached to this nitrogen only. So there is incorporation of more nitrogen. 3 nitrogen atoms putting together under a phenyl steric effect. So it is not also stable. So to repeat the current question and along with the correct answer, in the coupling reaction between benzene diazonium chloride and aniline in the presence of acid, the yellow colored dye A formed is para amino azobenzene, which is the fourth choice, that is the correct choice for this question. This finishes the current question and its answer. Now the 7th question, this reaction, so for reaction products were asked, here the reagents are asked. So in the reaction benzene diazonium, where benzene diazonium chloride gives rise to, that is meta-bromo-benzene diazonium chloride. This is meta product. So benzene diazonium chloride, ortho means adjacent carbon atom, meta means one carbon atom separate. So this is called meta-bromo-benzene diazonium chloride. In the reaction meta-bromo-benzene diazonium chloride, in the presence of some reagent, gives rise to meta-bromo-nitrobenzene or meta-nitro-bromobenzene, both mean the same. In this product, the reagent A is dash. They have given 4 choices. For first choice is phosphorus acid, H3PO4 is phosphoric acid. This is phosphorus, metaphosphorus acid, H3PO2. Second choice is in general acid, it is everywhere, it is acid. If it is specified like this, you can use HCl and HNO3 safely, because sulfuric acid may dehydrate, remove water. Nitric acid sometimes undergoes oxidizes the species, only mild condition, but rigorous condition nitric acid cannot be it will not disturb. So nitric acid or hydrochloric acid, if it can be used, it is generally mentioned as H+. Of course it is dissolved in water. Phosphorus acid specifically dissolved mixed with water. Third choice, mercuric sulfate, sulfuric acid, mercuric sulfate and sulfuric acid. Fourth choice, cuprous chloride, it is given. So in these cases, this correct choice is phosphorus acid, because phosphorus acid is one which causes the removal of this removal of azo group. If it removes azo group, only bromobenzene. On the other hand, if you just heat this one, it will give rise to bromo. Second choice. If it is heated with any acid in the presence of water, it will give rise to bromobenzene. It is not bromobenzene. It is meta-nitro-bromobenzene. If third choice is used, hydration is taking place. Some hydration means hydroxy substituted. So bromo-nitrophenol may form. This is named reaction. Halobenzene, it will be formed. Once again, it will give rise to halobenzene, not bromobenzene. Chlorobenzene may be formed. Meta-nitrochlorobenzene or chlorobenzene will be formed. Only if meta-nitro-bromobenzene to be formed, the correct reagent is H3PO2 dissolved in, of course, mixed with water. So, to repeat the correct question along with the correct answer, in the reaction where meta-bromobenzene diazonium chloride gives meta-nitro-bromobenzene in the presence of a reagent A, the correct reagent A is H3PO2 mixed with water. This finishes the current question and its answer. Now, the 8th question. It is based on the nitration of nitrobenzene. Nitration of nitrobenzene. So, here the question C6H5NO2. Question reads in this fashion. So, reaction is given. C6H5NO2 is nothing but nitrobenzene. C6H6 is benzene. One hydrogen atom is replaced by nitro group. Nitrobenzene, when it is treated with a mixture of concentrated nitric acid and concentrated sulfuric acid, actually temperature given is 80 to 100. Here we have condensed as 90 degrees centigrade. Temperature is specified as 80 to 100. So, the nitrobenzene when treated with a mixture of concentrated nitric acid and concentrated sulfuric acid in the temperature range 80 to 100 degrees C forms dash. There are 4 choices given. A is para-dinitrobenzene. B is ortho-dinitrobenzene. C is meta-dinitrobenzene. D is 1,3,5-trinitrobenzene. So here nitro group is a meta-directing group. Chloro group, we have studied that chlorohalogens are ortho-para-directing groups, whereas nitro group is meta-directing. Or in other words, how to remember these groups means that electron releasing groups, they will direct the further substituent in the ortho or para position. Electron withdrawing groups, they will direct the further substituent in the meta position. So this is also standard reaction. Nitration of this is nitration mixture. Concentrated nitric acid and concentrated sulfuric acid is called nitration mixture. Nitration mixture means incorporates nitro group. So nitration of nitrobenzene, it is a substitution reaction. Nitro group is a meta-directing group. So the resultant product is meta-dinitrobenzene. Meta-dinitrobenzene. Actually they have given IUPAC naming. Here it is mentioned as 1,3. Here it is mentioned as 1,2. Here it is mentioned as 1,4. Here it is mentioned as 1,3,5. So the correct question reading in this fashion, nitrobenzene in the presence of nitration mixture at 80 to 100 degrees C yields dash. First one is 1,4-dinitrobenzene, second one is 1,2-dinitrobenzene, third one is 1,3-dinitrobenzene, fourth one is 1,3,5-trinitrobenzene. They have given in words. So the correct choice is 1,3-dinitrobenzene. So to repeat the current question along with the correct answer is that the nitrobenzene reactant on heating to a temperature of 80 to 100 degree in the presence of nitration mixture, namely concentrated nitric acid and sulfuric acid, forms the product 1,3-dinitrobenzene. benzene. This finishes the current question and its answer. Now this question is also based on the reduction of nitrobenzene. So questions are always likely to be asked in the reduction products of nitrobenzene. So the reduction products of nitrobenzene depend upon the agent which is used. Strongly alkaline acidic medium or strongly alkaline medium, neutral medium, different reagents, good source of hydrogen. Depending upon this, nitrobenzene gives a variety of products. Already we have seen this type of question with a different agent. Strongly acidic medium we have seen. Now this question reads in this fashion. The product obtained in the reaction where nitrobenzene is treated with zinc ammonium chloride is dash. Zinc chlorine is used as the reducing agent. Here ammonium chloride, hydrogen is available, but now how it is controlled availability is selected with the different reagents. Hydrogen is to be available from ammonium chloride. Hydrogen is to be available from hydrogen as such, depending upon. So they have given 4 choices. That is C6H5NHOH. This is called phenyl hydroxylamine. 5 means C6H5. So this compound is C6H5NHOH. NH2OH is called hydroxylamine, in which one hydrogen atom is replaced by phenyl group. So it is phenyl hydroxylamine. Whereas this is azobenzene. Already we have seen C6H5N double bond N C6H5. Whereas this one azoxybenzene. This also we have seen in the ionic form. Azoxybenzene C6H5N double bond N plus O minus C6H5. Whereas last one is merely aniline. So in the zinc ammonium chloride reaction, it will be reduced to hydroxylamine derivative because amino group is there. Amino group is there. Amino group is retention along also in the ionic form NH4Cl. So this NH4OH is ionic form. So ionic form product is formed. Here this is also forming ionic product, but this is in a strong reducing agent. This we have already seen, azoxybenzene. So for this current question, the correct choice is phenyl hydroxylamine. It will not form azobenzene or azoxybenzene or aniline. So under this condition, it preferentially forms only phenyl hydroxylamine. To repeat the current question along with the correct answer, the product obtained in the reaction where nitrobenzene is treated with a mixture of zinc powder and ammonium chloride solution, it forms phenyl hydroxylamine. This is the correct answer for this question. This finishes the question and its answer, question number 9. Now the question number 10, our last question in this chapter, is that here it is given a reaction sequence. So far given only one type of reaction. Here it is given a reaction sequence. So question reads in this fashion. In the reaction sequence means series of reactions in which aminobenzene is treated with sodium nitrite and HCl at 0 degree centigrade. It forms initially a product called A. Then the product A is treated with C6H5N CH3 twice. C6H5N CH3 twice. This is called dimethyl aniline. NN dimethyl aniline. C6H5NH2 is aniline. C6H6 is benzene. C6H5NH2 is aniline. This aniline, the 2 hydrogen atoms are replaced by CH3. This is called NN dimethyl aniline. 2 methyl groups are attached to the nitrogen. So it is called NN dimethyl aminobenzene or aniline. Aminobenzene or aniline. So when it is treated with this compound, we get a colored substance E. A colored product E is obtained. In that case, what is the structure of E? The structure of E, the structure of the compound E is dash. They have given 4 choices. First one, coupled product. All are coupled product. So this is a reaction where coupling reaction takes place. So we have seen the diastization and coupling. So any aromatic primary amine, aniline is the simplest aromatic primary amine. Any aromatic primary amine, when treated with a mixture of sodium nitrate and HCl, which generates HNO2. NaNO2 plus HCl giving HNO2. HNO2 nitrous acid is used, ice cold temperature is used. This is the condition for diastization. So the product A is benzene diazonium chloride, C6H5N2 plus Cl minus. Now this benzene diazonium chloride is subjected to another complicated compound. So here it is a type of colored, it is given. Colored means dye. Dye means it is a coupling reaction. So benzene diazonium chloride undergoes coupling reaction. All are coupled products. C6H5NH double bond, C6H4 para position. So the first compound is C6H5NH double bond, NH, benzene ring, N, Me twice. That is CH3 twice. Here C6H5N double bond, this is NH. This one C6H5N double bond, N, CH3 twice or Me twice. Me means methyl group, CH3 twice. Last one C6H5N double bond, N, CH2 single bond, N, C6H5 CH3. So here it is there is a methylene group between 2 nitrogen atoms. That is the third structure C. Fourth structure is 1. See, here it is in the ortho position, that is CH3 C6H4 N double bond N, C6H4 ortho position CH3. So it is like these are the choices they have given. In all these choices, benzene diazonium chloride is initially formed. We have seen C6H5. So the product A is benzene diazonium chloride. It couples. Diazonium chloride means N plus Cl minus. The coupling medium is C6H5 N CH3 twice. Already we have seen during coupling, phenyl hydrogen, benzene hydrogen is removed to enable the para substituted product, which is the most stable. So para substituted product is C6H5 N double bond N. If you write the coupling reaction, automatically you can end up with the correct product. So in this way coupling reaction takes place, which is the choice B, correct answer. So C6H5, so 5 means C6H5. So C6H5N double bond, C6H5N double bond N, benzene ring, para position. So para substituted derivative is the most stable colored product. So this is the correct choice for the current question. So to repeat the current question, that is last question, along with the correct answer, in the reaction sequence where aminobenzene is treated initially with sodium nitrate and hydrochloric acid at 0 degree C, the product formed A is further subjected to the coupling with NN dimethyl aniline. A colored dye E is obtained. The colored dye is para NN dimethyl asobenzene, para NN dimethyl asobenzene. This is the name of the product, because this unit we have seen, this is asobenzene. In the asobenzene para portion there is amino group NH2. But the amino group, in the same nitrogen atom, two methyl groups are there. This is called para-NN dimethyl azobenzene. This is the correct product for the current question. So this finishes the current question and its correct answer.